Okay, welcome. Welcome to the next practicals of object-oriented programming. Is it loud enough in the very back? Yes, and also for you?
Yeah, I think so.
Okay, this also sounds good. Thank you. Okay, let's see what we do today. Last time at the very end, we started with the command pattern, and then we needed to hurry up, and maybe not everything was completely clear, so we'll repeat this and also extend it a little bit. Then we talk about teamwork, because you will need this in assignment 2, and in particular we will discuss branches on Git, which you should use because it makes your teamwork easier. Then last time in the lecture there were the exceptions, so we will discuss them today, and we show you one more data structure, which is the standard optional, which you can use in your assignment 2, which might be beneficial in some situations. Okay, then let's start with the command pattern.
Okay, so I'll just repeat the slides and then go over the code. So let's talk about the second approach. We created this command parser, then now you notice the abstract class for the command, and then we derive this with a help command for now. Yes, we saved these commands using a map, which maps the string, which should execute the command to the actual command class, which then executes the logic for this command. Yes. And we had this picture where we had this game. We register commands, then we send the input to the command parser, which then using the map looks up the command and executes, for example, the move command. And today we'll also implement that this move command can now change stuff in the game class, because you might need that. Okay, so let's quickly go over the code. I think maybe let's start with the command parser. Or the game. Let's start with the game. Here we created the command parser, then we registered the help command, and then we tried it out by passing the string help into this parser. And what this parser does is just insert the command into the map, and when we execute a string, it looks up if this command exists, and if it exists, we call add and then execute. Yeah, and we free it at the end. And let's have a look at the commands. Here we have this command class, and then we implemented this help command, which overrode the execute method. And like you last time learned in the lecture, we can now, because this is actually an abstract class, we won't be using this class directly. We'll always derive it and then use some child class of that class. We can mark this method as virtual, and now we know that we never instantiate this class because we don't want to do that.
Mm-hmm. So is the structure from last time clear to you? So basically, we distinguish the commands because we have this execute method, and the execute method is specific to the command that should be executed in the end. And there we use the inheritance, there we use the virtual method, and based on the class we can implement different logic that should be executed to the corresponding command. Okay.
Okay. Then,
yeah. We implement one more command to demonstrate this to you, because we have set up everything now. So we said that we need to register the commands first, and now we implement a second command which should print the player count. So the first thing that we want to do is we want to register a command, and we give it the name count. So if the user inputs count, then this command should be executed, and then we need to create a new command object, a new class basically. We will call this probably the count command. Okay, so the count command does not exist because we only have the help command and the abstract class command. So we need to create this additional class. Maybe I make it a bit larger. for you. Okay, so we create now the count command, which should, of course, inherit from command. We have some constructor. So this is the count command, which calls the constructor of the base class of command. Then we have the execute method. We need to implement this method then because it is now pure virtual in the base class, but we will do this in the CPP file. So yeah, I open this on the right side. This had the signature bool. Then we have play command.
Count command.
Count command. Execute. Then we do something here, and we can now assume that it will always work. So we have still a to-do here that's to be implemented. And we also need to implement the destructor of the count command. Yeah, probably it works, even though VS Code says something different. Okay, so now we have the game. We register the command to the command parser. And now when we execute it, then the input is checked. Then we go to the command parser CPP, search whether it is contained. And as we added it here, it is contained. And then we call the execute method on the command and should then execute the execute method of the count command. So maybe we print first count command here to see whether it works or not. And of course, we need to change the user input now that the user entered count, because we want to test the count command now. Okay, let's see whether it works. Okay, and as you can see, we printed count command now. So here, the execute method of the count command was executed and not of the help command and not of any other command. It was really the one of the count command, and that's why we printed this text here. So this works for now. Now we have a little issue because we want to print the player count in the count command, which we already implemented in the game. So there exists already a method in the game, print player count, which prints the player count of the game. And now we need to access the game object in this count command such that we can print the player count. So basically, I just want to call player count here on some game object, which I do not have at the moment. And that's why I need to pass on this game object to the count command. And we do this now in the constructor of the count command. There is one option to obtain the object there which we are in. And this is with the keyword this. So the keyword this gives me a pointer to the object where I'm currently executing at the moment the start game method. And so this is basically the pointer of the game object where the start game method is executed on. And I pass on now this game pointer to the count command. So I need to adapt the constructor of the count command. It now takes a game pointer. And we need to store the game now here. So we have a game pointer game. And once we have called the constructor of the base class, we also want to initialize it here. So we initialize the game pointer with the pointer that we pass on here. So now we have a game pointer present in the command HPP. And now we can call the game print player count method. One thing I forgot is, of course, we need to know the game here in the HPP. So the trivial solution would be that we include the game.hpp in this file. However, then we would have the situation that the game needs the command and the command needs the game. So they depend on each other, which would not work. Since we have a pointer, we do not actually need to know what the game is. We just need to know there exists this game class. And for that reason, we can just write there exists a game class. We do not include it. We do not know anything further about the game class except that it exists. And this is enough that we can use the pointer here.
It's like forward declaration of functions in C.
Mm-hmm.
Yes?
Has this any advantage over just including the header file for the game class?
Okay, the question was if this has an advantage over including the header file. The issue here is that we can't include the header file because maybe you can try it. I think you also need a semicolon in the command CPP.
Where?
In the command CPP.
Command CPP, okay.
So it compiles.
Okay, thank you. Okay, so first I include it now in the command CPP. Okay, here it's already included. And now we want to include it here as well. Game.hpp. Now we have the game HPP included in the command and vice versa. We need to include command parser and basically we also have the command here included. But I will.
Because command parser includes the command.
But to make it explicit, this is the situation. And now if we compile it, we have the problem in file included from command CPP, we are in command HPP, and the command HPP needs again a command. So we are in command HPP, game HPP, and the game HPP needs the command, but we are already in the include of command HPP. So this is a circular dependency here. Is this clear to you? Okay, and that's why it doesn't compile.
Yes.
And if we omit this line here and just have the class game, then we do not include the file, we just know there is this game, and this is enough that we can handle the pointer, and we get rid of this circular dependency, and now it compiles. Except for...
you need game underscore.
I need the underscore.
You can also think of the issue like without these includes, just that if the command needs to know what the game looks like, and for the game needs to know what the command looks like, this is impossible to do, to fulfill both. Because to know what the game looks like, we need to know, and so on.
But now with this trick, now it really works. It compiled, and it also prints this player count 2. So just to visualize this one more time, we are in the game HPP. We started our game. We registered the count command. The user inputs now count. We execute. We go to the parser and execute it with the input. The parser checks, is there a command called input? Is there this count command? It executes the count command. And in the count command, we say, okay, we go back to the game, call the function print player count on the game, execute player count equals 2, and then we go back to the start game and can do anything what we like. So we can read in one more input or whatever. Okay, is the structure clear? Like we have this kind of circle where we start from the game and then go to the command, and the command goes back to the game, calls a method there, and then we go back to the game and can continue from there.
Mm-hmm. Mm-hmm. So last time we touched on the advantages and the disadvantages. We already talked about those, but maybe you can now understand why we have this game command parser, then we have a specific command and then the game again, which might make it difficult to really, if you read the code, to see what's happening, because the control flow is is from the game to the command parser to the command, and then again to the game. Whereas with the other method, you just in the game distinguish between the commands and then call a method in the game, which is a bit more clear. But yeah, and again, the advantages is just that we have the logic more encapsulated, and we don't have to have these switch cases. So both have the advantages and disadvantages, and you can choose whichever one you like or create a new method if you want to.
So maybe we can switch back to the code for a second. So basically, if you implement a new command, you really have then here a huge part of the logic of the command implemented. So this is then not in the game HPP or game CPP, but it really just belongs to the specific command. So it's split up between the classes. If you would do everything in the game, then this file would get really long. It would have, I don't know, 1,000 lines of code. But this is an option to split up the project into multiple files where each file takes one functionality.
Yeah. And maybe you already now notice that adding a command is very easy because we just have to write this and then implement the execute and we are done. Yeah.
So kind of this structure also helps people to implement new commands fast in an assignment interview.
Yeah.
Okay.
Then let's continue with organizational matters. Yes, so let's first talk about the homework. We just published the grading. I think that's everything to homework 1. If you have any questions about your grading, you can always ask on Discord. Then the design discussions, there are 5 teams which are still not registered, but it is mandatory for you to participate. And for all team members to participate in those design discussions. And I think now many slots are already full. So
next Friday, so this Friday, next Friday, there are no empty slots. If somebody knows that he is not registered or she is not registered, or maybe double check that.
Yes. Okay, and then for homework 2, we now decided that it will start in 1 month, so there's still much time until then, and you will have 2 weeks of time, and I think it's about something pretty interesting because it will be about more advanced C++ concepts, which are not really part of the material that is like within the exam or you need with the assignments, but I think it could be really interesting to, for the homework to dive into that.
Okay. Then we come to a short section about teamwork. Maybe you ask how we grade the teamwork. So we use a tool called Git Reporter, which tracks the contribution of each team member. So it goes through the history of the commits in your repository, checks how many insertions, deletions every author has, also which lines survive until the end. And then we get some statistical overview of how much everyone is doing. This also keeps track of changes that are, for example, style guide related. So if somebody at the very end formats everything, then this will not be counted as a large contribution to the project. And we also see if somebody is just writing comments, for example. So if somebody is writing the documentation at the very end but does not contribute to the actual code, we will see this. So yeah. And the report is also available to you. So if you test your repository on GitLab and download the test cases, then you can also download the report from the Git reporter. So most of you are 3 people in the team, so we aim that everyone has at least 25% contribution in their team. So it does not need to be fully equal, so it does not need to be that everyone has a third, but like 25% should be the minimum here. And it's also important that everyone needs to commit. So this goes hand in hand with that. pair programming is restricted. So we really want to avoid the situation that 2 of you or 3 of you are sitting in front of one laptop, one is programming, the other 2 are watching, and then only one is committing the whole code. So if this is the case, and 2 have then in our tool like 5% contribution, then this will be a problem. So we really want you to sit down in front of your laptop and program large parts on your own. And of course, it's allowed if you, for example, merge 2 works. So if your colleague did something and you did something, and then you want to merge those changes together, then of course sit down together. Or if you want to fix a bug or do some small part, it's no problem if you do this together. But if you're doing large parts together in the project, this will be a problem, because at the end we want everyone to commit and contribute to the project. Yeah?
Will it keep track of who merges the branch in the main?
Yeah.
If I commit only one branch and we have one which is responsible for conflicts in the main, will it keep track of that main before?
Yeah, so when you contribute something to the project, and then at the very end you say, okay, I want to merge it into the work of the others, the Git reporter will keep track of these changes. However, if you merge something and you squash all the commits before, then there is no option to get to the commits. It's more an advanced question here. Yeah. So now the question is, how can you work together using Git in an efficient way? And that's why we want to introduce the Git branches here. Okay, so assume this situation. We start at the very left. This is now called the main branch usually. And now maybe you want to contribute to your project. Or let's say Julia wants to contribute to our project. So she would like to make some changes. So let's say we are on the blue line here, yeah? And at the very same time, I would also like to do something, yeah? So I'm now the green one here, for example. So I want to do a commit and a second commit. And now the problem is that these commits, like they are probably in a conflict, because you change the game CPP and I want to change the game CPP, and then you want to change this again, and I want to change it again, and so on. So every time we change something, we have some conflict. We have to look what was the things that the other person did, how can I now put these changes into my changes, and this is always challenging. And for that reason, we would like to split the workflow as it is drawn here. So we would really like to have that Julia can do her own thing for 3 commits, and I can do my own thing for 2 commits. And then once Julia has implemented their feature and I have implemented my feature, then we say, okay, how can we put those 2 features together? How can we merge those 2 changes together? And that would happen then at this green dot here, where we have Julia's last version and my last version, and we want to get to a common version. And that's where we use Git branches for. So a branch is just like this part here, eine Verzweigung, an Ast. And we have then multiple branches in the project, and whenever something is complete, we merge those 2 branches together. Die Zweige gehen also wieder zusammen, and then we have a solution, and we only have to think about merging changes together one time and not after every commit.
Yes, and sometimes this merging of these 2 changes even works automatically, but most of the time you'll need to do this manually, where you maybe with a few code snippets there are some conflicts and you have to select which one you want to keep or how you want to merge those.
Mm-hmm. Okay, and yeah?
Does it make a difference if we merge or rebase our branches?
So does it make a difference if we merge or rebase? It depends on the situation. So merging is always kind of you have those two versions and then you put them together, rebasing is maybe does not work all the time.
I don't know, with the Git report it should work. So if you want to rebase, you can, right?
Yes, so if the commits are preserved afterwards, it's no problem. Okay, then just a few commands to show you how this works. So if you execute git checkout and then your branch name, then you can change to a branch. Maybe you want to create a branch, then you also need to specify -b and then the branch name. This would create a branch. So for example, git checkout -b help command. And then it would be clear, okay, now in this branch we implement the help command. And at the very end, so if assume we are on at this node here, at the green node in the master branch, and this is now Julia's branch, then we want to merge them together, and therefore we have the merge command where we say git merge, and then in our case this would be Julia's branch that we want to merge into my branch. So we would call git merge and Julia then. And this merges the two versions together. And as you said, either this works automatically, you don't have to do anything afterwards, or you have now conflicting changes and you need to manually resolve them. Yeah, so that's basically everything about branches, and those who have attended VSB already know these slides. Do you have any questions?
Okay.
Then we continue with the next.
Yes, then let's continue with exceptions. Just a quick recap from last time. Exceptions are a way to early terminate a function. So if something goes wrong, you can throw an exception, which ideally would hint at what went wrong. And then at the function which called this function, you can then, with the try catch block, catch this exception and do stuff accordingly. So we have the try block, as I said, which where you can put your code which you want to execute, which might throw exceptions. And then in the catch block, you can specify what happens with which exceptions that this code might throw. Yes.
I think it's me again. So first example that you already know is the add method from the vector. And we also prepared something here. Just let me close everything. So, okay. That's vector. So remember, just comment out this part of the code. We have the array at the very top, or the vector here of size 6. So the numbers that are in the vector are the corresponding indices as well. And if you remember, if we call the add method now on some index which is not valid, for example 10, because we only have 6 positions here, and if we run this now, we see that we get this error message here, which says, okay, called after showing an instead of standard out of range because 10 is larger than 6. Yeah, okay, and this terminates the program now. And now, as you said, we can put this into a try block. And when we have this put this into a try block, we can catch this exception here. So we need a corresponding catch, and we catch a standard out of range exception, and with e.what we can print the error message. And if we do it now this way, then our program did not crash, so we see that we don't have this red arrow here, which marks that the program crashed, but everything is fine. and we printed with e.what the error message that is stored in the exception, which then tells us, okay, the size is our index was too large for the size. And then we can continue here with our program. For example, I don't know, I just print by, for example, and this is also then executed. So the exception which is thrown here does not terminate the program, but we can just continue because we caught the exception at this point.
Okay.
Yeah.
Then let's continue with actually implementing a custom exception and maybe throwing one. Yeah, I think I'll just continue in this file. Okay, what I want to implement now is a class which represents a non-zero integer, so an integer which is not zero. We might need this for, I don't know, division or something. So I'll create this class, non-zero integer, which will just store an integer value, and then we will have a constructor, which now we want to check if this value we pass here equals 0. And if it equals 0, we want to throw something. And to do that, we'll now implement a custom exception. And we'll call this, oops. We'll call this 0 exception. And this 0 exception will derive that from the std exception, like this. And we do it public, and now we can also override the what method. So yeah, so this returns a const char pointer, and it's constant, it's no except, and we'll override that from exception. So yeah,
that is really long. Maybe you can explain what each of them is.
We return a message which is a C string, so not a C++ string, which is probably because they can also throw exceptions. And this what method is also no except because we don't want to throw an exception when we are already while throwing an exception. It's constant because we're not changing anything within this exception, and we specify override to really make sure that this is the what method from std exception and not something else. Okay. And we'll just return value is 0. And we can now specify the 0 exception here. Like this, and now we throw our custom exception, in here. And else, if the value is not 0, we assign it to our value which we have stored in this class.
So I think you need here non-zero int in the constructor.
Oops. Okay, then maybe let's try this in the main. We'll create a non-zero integer. So call it just I, and then pass 0. And let's check if this worked. Yes, so we get here the program terminated because we threw an exception, which is the 0 exception, and the what value is 0, because that's what we're returning here. So this worked.
Mm-hmm. Okay, then how can we catch the exception? Okay, that's basically the same as with the vector before. So we put everything into a try catch block. So we create now our no-zero integer in the try block, and then we catch it. So we catch the 0 exception, and I don't want to print the message now, I just print 0 exception here. And let's see whether now our zero exception message is printed and our program does not crash anymore. Okay, and this is what happened here. So we have main and zero exception was printed, so we successfully caught the exception here. So if we look back to the exception here on the very top, we see that the zero exception inherits from the standard exception. And now let's try what happens if I do not catch the specific zero exception, but the more general standard exception. So let's see whether this is also caught. Okay, and we also see it's we go into the catch block and we print this zero exception here. Okay, so we can either catch the exception if we use the corresponding type, or if we use a type from when it's derived. Now, maybe we do something more here. We have the zero exception. Print here zero exception. And here we print the standard exception. What happens now? Has somebody a guess? Yeah? Zero exception is outputted, you say? Okay. Let's give it a try. Yeah, zero exception is outputted. Okay, then maybe we change the order. So we put the standard exception now before the zero exception. What does now happen? Maybe somebody else, but thank you. Yeah?
Standard exception.
Okay, you say standard exception is printed. Let's see. We already get some warning. Maybe we read through it. Yeah, standard exception. And already the warning says, okay, an exception of type zero exception will be called by an earlier handler. So this specific zero exception is after some base exception from where it inherits, and already the compiler warns us that this part of the code will never be executed. So this is very convenient here. Okay, I think that's it. Next example.
Yes. We don't have any slides, right?
I think one line. Do we have one line? Yeah.
Yes, okay. So we'll now look into how we can handle these bad alloc exceptions that are thrown if we try to allocate memory dynamically in C++, but this somehow fails. So this is the same as malloc returning a null pointer in C. We'll now look into how this works in C++.
I think you can just continue where we were.
Then let's delete everything. Okay, so, and we now just have two methods. One where we just do some allocation, and the main. Here we'll call this, and in here we'll just have, let's create first an int pointer out here in the main, so I'll call this p1, new integer with the value 5, and then delete it again, like this. Then I'll also create two integer pointers in here. Like this. Okay, so yeah, I think this looks okay, but in C we always checked for zeros, and if some malloc returned a null pointer, we always had to freeze stuff that was allocated before. And maybe we'll look into this now. What happens in C++?
Yeah. So what could be a first approach? Okay, we see we have many news here. So maybe I just insert my try block here in the main function, put all the stuff in it. Then we catch the standard bad alloc, print, I don't know, out of memory. Okay, looks fine.
Yeah. So maybe we want to provoke new to throw such an exception.
Okay, so maybe we do this here.
Yes. So let's create a really large array.
So okay. So now we have the other type of brackets here to create an array, and now. So how many bytes are these? This is 1 kilobyte, 1 megabyte, 1 gigabyte, 128 gigabytes, if I did not miscount. So it's really large, yeah? And now let's try
You also need the array delete.
Yeah, I need to delete the array. Okay. Compile it, run it. We print out of memory, so this really was too large that we do not have that much of memory. And we print the out of memory here, and everything is fine, right?
Well, yes, but if you want to do it like in C, where we really freed everything all the time when our program exits, right now we are leaking 2 integer pointers.
Okay, which integer pointers do we need? Do we leak now? So integer pointer P1. Okay, we allocate it. I allocate stuff, integer pointer P2. Okay, those 2 were successful. Then we have the problem. And then we stop the execution because we throw an exception. And we directly go to the catch block and print the out of memory. So we skip this line here. We did not delete P1. And we also did not delete P2. So we have 2 memory leaks now. Because, we just catch it in the main and do not free anything in this case. Do you have any solutions for that?
I mean, yes. So maybe let's try to do it like we did in C, where we really have one try catch for everything. So the first thing we need is we need to move this delete out of here, like this, because now, even if ialloc stuff throws an exception, we'll still delete the pointer we created up here. But this new can still throw an exception, so we need to wrap it with a try catch. So let's do that. Let's write a try catch for the bad alloc exception. And maybe here print out of memory in this method, and here just print that we ran out of memory in the main. Let's just say out of memory main. Okay. Oops. So now we prevented this pointer from leaking, and we're also catching this bad alloc exception that this new can throw. And then this method can throw a bad alloc exception. We are logging this here, then we're deleting it. So in the main, everything seems fine, but we're still not freeing this integer pointer here when this one throws a bad alloc exception, because we're allocating it. Here this throws an exception. We exit out here, catch it, delete this pointer, and then exit the program, but we never deleted P2. So in here, again, we need a try catch around this one. Okay, and now I think that with every allocation we did, okay, I did this the wrong way around. With every allocation we did, we're now catching the correct exception and also freeing the correct pointers. Because if this goes out of memory, we are throwing it, we don't need to delete it because it didn't work, but we are deleting the P2 pointer. If P2 fails, we are exiting, we don't need to delete these two because they never existed, but we are deleting P1, so every edge case is handled, right? So let's try to compile it, and as we expected, we get the innermost message here. Maybe also something we can do here is to then signal that this program is out of memory. Let's rethrow this exception in this catch block here, so we can also handle it out here. And we also need to do this here. Yeah, right. Okay, now we would leak this, right?
I think, yeah.
Yes, so we
have
can
to
do this.
think about it one more time. Maybe the question first.
Yes.
Maybe something like a finally keyword in C++ also?
No. Yeah, this would be ideal, but this doesn't exist in C++. So I think we can't rethrow it. So I think, so a finally keyword in C++ doesn't exist. And I think we can't rethrow this exception to signal we are out of memory.
We can't
right?
rethrow it here now
because if we throw in here, we are never deleting P2. So if we want to rethrow it,
then
we would also need to do it in here.
Okay. Where
Yes.
do we end up if we rethrow it?
Yes, if we throw this exception here, we go into this catch block, where we can also rethrow it, so we get into this one, but we do need to delete P1 here, which is what is still left from up here. And
Now-
if we do it now, now we're really exiting the program in the main how we wanted it to exit, because we are out of memory.
But it seems really difficult, right? So we have now, how many triplet catch blocks do we have? 3?
3, yes. So practically for every pointer we are creating, we need to one try catch block to handle the out of memory. Even if it's not directly with this pointer here, we need to handle it outside when we call this method.
So for me, it seems a bit too difficult
Yes.
at the moment. But it would be the right solution. What we do now, we want to change those integer pointers a bit. And we assume for the next extension that we do not have integer pointers directly, but we have a class which is responsible for some memory. And we will see that this makes it a lot easier. How to deal such pointers, so if we just have an integer pointer here, how to deal with those, that's part of the lecture next week. But we will move those integer pointers now to a class.
Yes, so and we think we're using a trick here because when we throw an exception we are exiting from this method to the upper one, also all the structures of the objects we have in this class are called. And therefore, if we have an integer pointer class like that, where we store our pointer and the destructor deletes it, we are always freeing this pointer, even if we are exiting this method by throwing an error.
Okay, I just need to cheat. I don't know the class, but it's very simple. Yeah. So we have this, and then we are not lazy today and delete also the copy constructor and p. Okay, so we have now just the integer pointer class, which has an integer pointer that is created at the beginning and is deleted in the destructor. And now my claim is that we can remove every try-catch except for the one in the main. So start here. We substitute now this with our integer pointer p1, and I think 5 was the value. Then get rid of the try here. Just allocate the stuff, get rid of the catch block, get rid of the delete because we have a destructor, So we have out of memory main, okay. And in the ialloc stuff, we create an integer pointer p2 with the value 10. Get rid of it. Okay, we have only implemented the integer pointer for a single value, not for an array. So I keep the array as it is because it will always now throw the memory error. But of course, we could do the similar thing for the array. Then we also get rid of the catch block, get rid of all the deletes. And now it looks much better. So we just have the integer pointer, we call the function, this is in the try catch, we have the integer pointer p2, and now the thing that fails. And now if we execute it again, we have out of memory main, and of course, this integer pointer is destructed after we leave the try block, and for that reason the destructor is called and the memory on the heap is freed. And also for this pointer, once we leave the alloc function, even if we leave it here because the bad alloc exception is thrown, the destructor is called, deletes the memory of p2, so we do not have any memory leaks here, and we got rid of all those try catch except for the one in the main function.
Yes. The idea, you will just have to trust us because Valgrind won't work with bad alloc exceptions if they are thrown by new, and it will always report a memory leak. So we can't really check, but we won't dig any memory here.
So basically, if you implement your classes and you implement a proper destructor and you do not allocate memory outside, there is no problem. It's enough to have this try catch in the main.
And I would also argue that this construct with this class, which constructs the dynamic memory and then frees it with the destructor, is also easier than trying to figure out all these try-catch blocks where you need to catch in bad alloc exception, where you need to rethrow it, and then what you need to delete and everything. This would be the same headache as we had in C, when we all had all these null checks, and just with this class where we put all our dynamic memory in some classes where we then call it destructor, this wouldn't happen.
And still, if you want to use something like integer pointer here, the solution for that will be shown next time in the lecture, so next week.
There is already some C classes which we just demonstrated here for us, so we don't have to implement this all the time.
So basically like this class, but a bit more advanced and a bit better to use. Yeah?
Technically, delete isn't the same as free. If I just put everything in my main function and I allocate every integer pointer there, and if I just use free delete sequentially, wouldn't this also work because delete doesn't cause a double free?
So the question was if free and delete are more or less the same or not the same, but if you delete something twice, then you also have a double free. So delete is just a wrapper around free. Delete can do more than free, but you can think about delete as it would call free internally at some point. So also the new, in our case, it creates this integer object, but when the memory is allocated, it calls malloc. And also the delete calls the destructor of the object, but it also frees the memory, so it also calls free. So a delete does more than free, but the free is still in the delete. So also have the double free problem.
And I think with the second part of the question, if you put everything in the main, if you would just need one try catch, then yes, you would only need one because you only have it in the main, but this would be the same as in ESP last semester. If you malloc everything in the main, you only have to do null checks there, but I don't know if this is really better.
And still you have to consider the case that the first allocation was correct and the second allocation went wrong, and you have to free the first one. So you still kind of need some structure there to free everything.
Yeah. Okay, then...
Maybe some more fun part now.
Yes.
Okay.
Yeah, I think you will start with presenting the existing code.
Okay. Just let me go through the slides if everything, we did hear everything. So we already discussed this. Yeah, okay. So we are not standard optional, but we have prepared some code. So we will demonstrate this to you now. So we have a class entity which does nothing, it just exists, and let's assume this could be a player or, I don't know, a monster or whatever. And then we have a class map, which consists of a vector of entity pointers. So it's just a one-dimensional map, so I don't know, 5 fields next to each other. And when the map is constructed, we have a size of 10, and each field has a null pointer. So we have a vector containing 10 null pointers. Then we have a method where we can set an entity. So we pass on an entity pointer and set it at a specific location in the map. And there is also the option to get an entity. And what do we do there? We check the location at the map, whether it's a null pointer. So null pointer indicates there is no entity at this location. We throw the standard runtime error because it's an error. Yeah, nothing is on the map. And otherwise, we return the entity, so the object which is located at the specific position on the map. And then we also have a function find entities. So it just has a vector of entities which is empty at the beginning. We iterate over the map, try to get the entity from the first position, second position, third position of the map, and so on. If this works, then we push it to the entities vector here. We print something, and otherwise, if we have the runtime error, yeah, we said in the get entity method there could be this runtime error, then nothing is on that field position, so we print the exception and continue with the next position. And then we have a main function which just creates the map, sets an entity on the 0 and the 5th position. So we have 2 entities there, and we try to find the entities. And again, if we iterate over the positions at those 2 indices, we will get an entity. And in all other cases, the exception is thrown, and we will print the exception. I can also execute it, right? Mm-hmm. So we are in the optional, and we call... Do we have a makefile? No. So we call the main, and if you think back at the position 0, we set an entity, so entity found at position 0, then we have 4 times an exception, then we have the entity found at position 5, which we set here, and then all the remaining positions are again exceptions. Okay. I mean, there is a problem with that, right? So we have this exception very, very often, and the entities only on very few things. And I mean, it's rather normal that at the position there is no entity set, no player, no monster, whatever. So I would say that in this program at this point, we should not use an exception because it's not something special. It's not an error that is happening. It's just normal behavior that there is no entity at the position. So we should also treat this as a normal situation and not as an exception where we always throw an exception. Now the question is, what is a better solution for that?
Okay, so of course the first thing we could do is just return a null pointer from get entity if there's no entity here. But I think this is a rather ugly solution, and there is something better in the standard library, namely the std optional. So what is our motivation? Well, we want to represent some value which can either exist or it can't exist. So like already the name tells us, we want something that is optionally there or not. And yeah, and this optional is just the wrapper around this value. So which methods do we have? Well, we have 2 constructors, one which is just empty, so then there is no value, and one where we pass a value. so then this optional isn't empty. Then it also has the method hasValue, which can check if an optional contains a value. And then the value method, which returns a value if it is available, or else throws an exception if there's no value in the optional. So ideally, we would first check if this has a value, if this optional has a value, and then if it has a value, we can safely use value and know that no exception will be thrown. Okay, so let's implement that. Yes, first we need to include it. And now, instead of directly returning this entity pointer here, we'll create an optional of the type entity pointer, and we'll return that. And instead of throwing an arrow here, if it doesn't exist, we'll return this std optional and call the constructor with no parameters, because we want it to be empty. And down here, we'll create the optional like that. So we want a value in here. Is there something?
No, that's just my Visual Studio Code.
Okay.
Just ignore it.
And then in this find entity method, or maybe first, in C++, you don't always need to write this when calling a constructor, when returning from something where we already know the type. You could just omit this, and then your code would just look like this, which is maybe a bit more clean. So here we know this is empty, and here we know we're calling the constructor with one, with a value in the optional.
So this can basically be deferred from the return type.
Okay, and then down here, instead of this try catch, we'll get this entity. We'll call it get entity with I.
It's fine. Just ignore it. Now the problem is that standard optional is, I don't know, since C++ 17.
Okay, yeah.
Is it, or 17, and my VS Code is, I don't know, C++ 11, and then it does not recognize the optional.
Okay,
so
yes.
Just ignore it.
So, and now we can check if this entity, with this hasValue method, if this optional has a value, and if it has a value, we can add this entity here. And if it doesn't have a value, we'll just do nothing, because we don't want to do anything in that case.
Maybe you can print something here as well. The colon.
Oh, okay, yes. And maybe now let's run it. Okay, I think
specify C++ 17.
we need C++ 17 for optional to work. Okay, now it compiles. And when we execute it, okay, we can see that entity at position 0, and at position 5 it finds an entity, and otherwise we're not constantly throwing an exception if there's no entity.
So is this then more efficient?
Yeah, this could be more efficient because exceptions are rather slow. But this is not the main problem. The main problem is that exceptions are really only for exceptional cases and not when you're expecting to get an exception. Yeah, I just have a few more methods which you could use. Namely, that if you use an optional like a Boolean, it has an implicit cast to Boolean, and it's the same as if you would call hasValue. So instead of calling hasValue here, we could just do if entity, and then it's true if it has a value.
So this is basically the same as we would have a pointer and just write if pointer and see it's no null pointer.
Yeah. And you can dereference an optional more or less, you can use the dereferencing operator, which will then return the value of the optional. Yes, and then if you dereference an optional, you have to be sure it exists, because if it doesn't, it's just undefined behavior, so you don't know what happens.
So it's better probably to use the value method.
It's better to use the value method, but because we already checked here, we could already also just dereference it and get the value like that. And maybe let's try to compile it and execute it, and yes, this still works.
Very nice.
So this, that we shouldn't throw any exceptions during normal program flow, is something that also depends on the context of how you use the function. For example, this getEntity, here we are using it to find entities in this map. And this is, of course, where we shouldn't use exceptions because they would constantly get thrown. But if we would call this getEntity function only with user input, which we expect normally to be correct, then this could be fine to throw an error in there, because then this error would only get thrown when the user enters something wrong. And when the user enters something wrong, this would be a case where we can use exceptions. So this is also dependent on context, how you would write such a method. Yeah, this is what I said. And do we want to do the last thing in here?
We have 7 more minutes, so...
Yes, so I'll now create some method which now gets an entity pointer based on user input. So I don't know, let's call it read from user, like this. We read just an index. I'll just do it like this. We need the map. And now we could just do getEntity at the index, but we would now need to handle what happens if this entity doesn't exist. But as we said, when we read from user input, it's fine to throw an exception if it's wrong, because we would normally expect it to not be wrong. So right now we could just call value on it, and this would throw an exception if this entity doesn't exist. We can also try this.
You need to call a function.
Yes, I need
somewhere.
to call it. Read from user and pass the map. I would need to return this. Okay, and if I now input position 0, this works. And if I input something that's with the wrong index, we get this exception, bad optional access. Ideally, in your program, you wouldn't throw that exception, but maybe have an if here. If this optional has a value, then you throw some entity doesn't exist exception and not just use this exception from the standard library. But else this would be fine, because we would expect user input to be correct.
Should we also show this?
Yeah, we could do it. So if, let's first save this entity. Maybe this time I could also specify the type here, just so that it's clear that we are talking about an optional with an entity pointer. And then if the entity, if this this implicit conversion is false, so this has no value, we could just throw, I don't know, a runtime error and say no entity.
So this runtime error is basically an exception that is already provided from C++ for us.
Yeah, as I said, normally you would create your own exception like we did at the beginning. And now we can execute this. And if I input something wrong, we get this runtime error exception instead, where our message is that we have no entity there. So yeah, this would also be a way to do this. So optional really provides you with a way to either has a value or you don't have a value, and you also have a way to raise an exception if we don't have a value. Okay.
Maybe go back to the code, and so to the map class. So we said the map has now a vector of entities, and if there is no entity present, it's a null pointer. So could we also use an optional there?
Yes. So which I just used the pointer here because I needed something which can represent either an entity or nothing, in our case the null pointer. Instead, here, we could just save it in the map with an optional, and now we don't have a pointer, but we really have the entity stored in this vector, or nothing. And then here I don't know if this now works. I hope so.
Probably need some other constructor then, but...
Yeah, but we need to dereference the entity here, so we're copying it, and here we can, instead of returning a pointer, we can return the entity. Yeah, I would need to do remove these pointers here.
Yeah, I think we don't need to try it out, but just for the concept, okay. You can also use the optional already in the map.
Yes, so this would be, I think, the best solution now, because having these pointers in the vector is a bit weird, because we don't know where these point to. Here it's just to some memory in the main function, but if we want to have dynamic memory, we would also need to do this. But with this optional, we can really just store here optional entities, which are directly in the vector instead of somewhere else.
Okay, are there any questions?
Yes?
Is there any method which you can override to make it implicit cast equal to Boolean or any other vector?
To what? Sorry.
Boolean or integer?
Oh, yes, we will learn about this in today's lecture. I don't know if this specific example, but generally how to do stuff like this will be covered in today's lecture.
Any further? Yeah.
Is it allowed to use these errors, runtime errors, something like that in the assignment?
So the question was whether it's allowed to use a runtime error in the assignment. And yeah, it is allowed, but it's better if you write your own exceptions, because you can also achieve 2 points for writing an own exception class.
Mm-hmm. Okay.
So can I make a very good Überleitung into the lecture? Because we have seen here this operator here in front of the entity, and optional is not the pointer, but we can still dereference it. So we have this dereferencing operator, which has now a completely different purpose. And exactly that's what David will talk about in today's lecture. And I think we will start in 10 minutes with the lecture 25. Yeah. Okay, so you have 10 minutes break, and then the lecture starts.
Okay.
Thank you.